Okay, right, so I think we're all here. So, good morning, everybody. So, silence, that's good. Right, this is called Lecture 7, and it's called Algorithms. Now, last lecture, we did, I think, it was the most important lecture I taught you because it was about if statements, and I tried to show you that basically if you get if statements wrong, the consequences can be really bad. So in some ways that was the most important lecture of this series. And I think this lecture is possibly the most conceptually difficult to understand, because what we're going to do is we're going to use if statements, arrays, variables, loops, and we're all going to bring all those things together, bring all those components together, and we're going to do or make things called algorithms. Now, having said that, what I've done is I've tried to break down these algorithms into very, very simple steps. So if you concentrate throughout this whole lecture and don't miss any steps, you'll be able to understand it and it won't be a problem. But if you sort of get distracted for a bit, you might miss it and then you won't be able to catch up with the thread. Having said that, if throughout this whole lecture there's any questions, if any of you don't understand what's going on, just put your hand up and shout, because if you think that's the case, and other people will also think that's the case. So we're going to do this together. And just tell me, make it interactive, so tell me if you're not getting something. So, with that said, Lecture 7, Algorithms. Right, here's an overview of today's lecture. Firstly, we're going to do a recap of last lecture, in case you weren't there. Then we're going to look at coursework 2 very briefly. Then we're going to move on to algorithms. And we're going to look at sorting numbers, so a sorting algorithm. We're going to look at an integrating algorithm and a differentiating algorithm. And then we're going to look at something called canned algorithms. That is a word I've made up, but it explains quite accurately what I want to talk about. So last lecture, I equated the idea of matrices and arrays. And I said that a matrix is basically an array is basically a matrix. So matrix is basically a mathematical word that mathematicians use to describe an array. And an array is the computer scientist word for the same thing. So they're completely interchangeable. And I taught you effectively, or I just told you, I didn't teach you because you knew it already, that if you want to do matrix algebra, so multiply, add, divide matrices, you can use all the exact same symbols or that you've used previously to add and multiply single numbers. And I said you can use the multiply, the power, the minus, and the plus, and also divide. I also taught you two new commands, which are the det command, which is for determinate, and the transpose, which is the single comma. And I said, effectively, MATLAB's a massively powerful tool to handle matrices and really use it to your advantage as an engineer. And then we looked at sort of basically if statements killing people. So, you know, if you get them wrong, bad things can happen. And we had a little play with a sort of muffin example. And we wrote some code together and we learned about these if, else if, else end statements. So what happens here is we've set the variable weight to 80. If weight's bigger than 40, it displays too heavy. If this isn't the case, it moves on to the next if statement. So else if weight is smaller than 30, display too light. Else if weight equals 0, there's no muffin. Else disp perfect, so it's the perfect weight for a muffin. And we sort of looked at building else if, or sorry, if, else if, and else statements in the class, and we had a little play at that. And I hope you've had a go at that in the examples class. So, sorry. So now I'm going to talk about coursework 2 very briefly. So I've slightly shifted the deadline to give you a little bit more time. So I think the original deadline was like the last Tuesday of term. I've moved it to the last Thursday of term because I want to give you the maximum amount of time to do it. And I've not put it on the last day of term because that's just evil. Like, you know, you're going to be at parties on the Thursday night. So 3 p.m. Thursday to make sure your Thursday night's free, basically. And again, I could have put this in January, but that's also quite mean. I don't want you working on this over Christmas, because that's all I don't want, you know, that's a nasty thing to do. So last Thursday of term, 10th December, 3 o'clock. And I'll put a Moodle link so you can upload it very shortly. So algorithms. Now, I firstly want to tell you what algorithms are. How many of you think you know what an algorithm is? Put your hands up. A few? Okay, so I'm going to explain it in sort of the official terms and then my terms. So I looked up on Wikipedia and Google what an algorithm is, and it said a computational procedure for solving a problem. And that was a bit long-winded. I didn't really understand it. So I redefined it as a handy piece of computer code that does something useful for you. So a handy piece of computer code that does something useful for you. And algorithms are everywhere in your daily lives. And I'm going to try and show you some examples of algorithms that are used. So our definition is a handy piece of computer code that does something useful for you. So how many of you have used Apple's Siri, or whatever it's called, and you speak into the phone, and then it does something random? Yeah, you got that on your phones? Or if you've got an Android phone, I think it's called Google Voice. Well, that's driving this is an algorithm. So in Google Voice, it's got a piece of code called an algorithm. And you give this algorithm speech, your voice, and it turns this into text, or tries to turn it into text. So you put audio data in, and you put it into Google Voice Search or Siri or whatever it is you got on your phone, and it spits out text that is then Googled. So this is an example of an algorithm. So a handy piece of code that does something useful for you. That fits that definition quite well. Another example of an algorithm might be the algorithm in the guidance system of a cruise missile. Into the algorithm, you might put the desired destination or the target, and then the algorithm will change the engine power. It'll move the control surfaces to make sure your cruise missile gets to its target. So this is an algorithm again. It's something that's taking sort of input and doing something. So it's, again, a handy piece of code that does something useful for you, okay? Another example that's been in the news a lot with this sort of NSA spying thing are encryption algorithms. So whenever you want to send information to your bank, so you know when you want to transfer £10 to your friend or whatever, you log into your banking website and they use an encryption algorithm to make sure the connection between your computer and the bank is secure so nobody else can read it. So it takes like it takes like whatever you want to do, scrambles it so nobody can read it and transmits it. So this is an example of an encryption algorithm. So you send your secret message to your bank, use an encryption algorithm to make the message unreadable, and then your bank can read it. So again, this is a handy piece of code that does something useful for you. So as you might have guessed, there's thousands and millions of different types of algorithms I could teach you about. And I thought, well, which ones am I going to teach you about? In this 1 hour, I've got to teach you about algorithms. And you know, we could have done encryption algorithms, we could have done Fourier transform algorithms, really fancy algorithms. But I thought I'd try and teach you the most 3 important algorithms that I think exist. The first one is a sorting algorithm. So this is to sort lists of numbers. And I picked this because it is a classical algorithm that everybody learns when they first learn to program a computer. And the reason for this, it's got all the components that you've learned about MATLAB already. So it's got if statements, it's got for loops, it's got arrays. So it's all those things into one little nice package, and it really is sort of the ideal example of an algorithm. So that's why I'm teaching that to you. So, and it's probably the most difficult algorithm you're going to learn. It's not that difficult. And then I'm going to teach you about an integration algorithm, because integrating is a useful thing to do that all engineers have to do. And at the moment, you can do sort of analytical integration, so you can integrate, cos or sine or something. And this will enable you to integrate any function. And as we're doing integration, I thought I'd also teach you about differentiation, because that's sort of the inverse of it, and it's also incredibly useful. So those are the 3 I'm going to teach you in this lecture, and they're not that difficult. But you just got to pay attention. So, sorting algorithms. Now, sorting algorithms are used all over our society. So if you open your phone and you look for your friend's name, you flick up the address book, it's all listed in alphabetical order. So somebody has written an algorithm to sort those names into alphabetical order. Or if, for example, you're writing a phone book, you'd want to sort the names in alphabetical order. A slightly more complicated sorting algorithm might be priorities on the NHS waiting list. So if you're going in for some cosmetic surgery on you to make you look a bit more pretty or something, that's probably not very important. But if you've got a life-threatening cancer, that's very important. So somebody in the NHS has written a sorting algorithm to sort the importance of the operation. So the critical operations go first, the less critical operations go last. So that's another example of a sorting algorithm. There's lots of sorting algorithms that are used all day, every day, and you don't necessarily realize it. So other examples are sorting scientific data and playing with playing cards, or sorting playing cards. So these are sorting algorithms. So the idea of a sorting algorithm is effectively to take a list of something. So here we've got 2, 4, 1, 3, 7, 5, 6, and turn it into an ordered list. So here we've got 1, 2, 3, 4, 5, 6, 7, or 7, 6, 5, 4, 3, 2, 1. So it's to give order to something. And reasons you might want to do this in scientific data, for example, is because if you collect sort of a muddled list of data, sometimes it's quite difficult to find the exact piece of data you want. So you might want to sort this list to give you very quick access to it. That's one example. So, rather than tell you what the bubbles... So this is an algorithm called the bubble sort. And rather than tell you how this algorithm works, I thought I'd let you figure it out for yourself. So I'm going to show you a video. what I want you to do, we're going to see some Lego men, okay? And they're going to build some towers. And the towers are going to be of different heights. And I want you to try and focus and try and figure out what they're doing. What is their procedure for sorting the Lego blocks in height order? So try and figure it out yourselves in the first iteration, and then we're going to watch it twice, and I'll show you or tell you what they actually do. So here we go, roll Lego men. So here are the blocks, and here are the little Lego men that are doing the sorting. So just watch what they do. So this is called a bubble sort. So can you see they're getting more ordered? A lot more ordered now. Almost ordered. And that's it. Now what I'm going to do is play at double the speed now. So if you've not figured out what they're doing, maybe playing at double the speed will help you. Okay. Now run off. Pretty cool. So let's watch this again. Go. This is twice the speed. Just watch what they do. Who knows what they're doing? Hands up, who knows what they're doing? Okay, so I think most of you got it, so this will end in a sec. Okay, so. Right, I think we've had enough of that. So. So, that is a bubble sort. That is a serious algorithm that computer scientists use to sort data and engineers use to sort data. So this is how it works. Okay, this is like the algorithm broken down into words. Start at the left-hand side of the list. So we started, all the men start on the left-hand side. Examine a pair of numbers. So we examine two blocks. Okay? If they're the wrong way around, so if they're not in the order we want, swap them. If they're not the wrong way around, leave them. Move on to the next pair of numbers. Repeat until the end of the list has been reached, and then we go all the way back up to the start, and we do it again. So examine a pair of numbers. If they're the wrong way around, swap them. If they're not the wrong way around, do nothing. Move on to the next pair of numbers. Repeat until the end. So basically, we just go through a list again and again and again, just swapping numbers until the right way around. And then if we do this enough times, the list will become ordered. So this is the classical sorting algorithm that all computer scientists and engineers, this is the first algorithm everybody learns. So here it is in sort of number form. So here's iteration 1. So this is like the first go at it. So we have the numbers 15, 8, 1, 5, 3. And we look at the numbers 15 and 8, and we basically swap those. So we go bloop, and we now have 8, 15, 1, 5, 3. We now look at 15 and 1. They're the wrong way around, so we swap them. We now have 8, 1, 15, 5, 3. We now look at this pair of numbers, so and we look that they're the wrong way around, so we swap them. We now have 3 and 15. Then we go back to the beginning of the list again, and we have 8 and 1, which is the wrong way around, so we swap them. We now have 8 and 5, which is the wrong way around, so we swap them, and we have 5 and 8. Then we look at the next two numbers, we have 8 and 3 the wrong way around, we swap them, we now have 8 and 15. So you can see the high numbers being always pushed to one side of the list, and the low numbers are always being pulled to the other side. And then we go round and round again, basically the list becomes more sorted and more sorted. So the trick is only swap them if they're the wrong way around. Any questions on that? Anybody not understand? If you've got a question, just shout. You look puzzled, or is that not true? No? You're not puzzled? You're happy? Okay, good. Fantastic. Right. So this is the example of the sorting algorithm. Now, if you remember back to lecture 1, I said the most difficult part of programming a computer is not remembering the commands or typing or anything like that. The most difficult part of programming a computer is basically breaking down a difficult real-world problem and figuring out how you implement that in MATLAB. So it's like, so you now understand this algorithm, you get it, but now the top problem is turning that into MATLAB code that works. So that's what we're going to do. Now, my biggest tip for turning complicated algorithms into real working code is write really tiny bits of them. So just write a little bit and see if it works. Then extend it a bit more, and then see if that works, and extend it a bit more. So go round and round and round, and just try and expand it very, very slowly, checking it works all the time. Is that hand? No? Okay. Okay, good. So when writing something complicated, do it bit by bit. So this is what we're going to do together. So, this is a little piece of code to swap two numbers. So at the very heart of our bubble search algorithm, our bubble sort algorithm, was the idea that we had to swap two numbers. Okay, so swap one number and the next. And this is the code to swap two numbers in MATLAB. So here we've got an array. We've got an array of 3, 2, 1, 5, and 4. And notice I've color-coded the 3 and the 2. So the 3's red and the 2's blue. This is just to help you see what's going on in the code. Then we've got I equals 1. So I've just set I equal 1. Okay? So now we go temp. So temp is a temporary variable. Okay? And we store in temp numbers brackets I. Well, I is 1. So what this will give us is this will give us the number at the 1th position in the list. So temp will be equal to 3. So I put on the right-hand side here in the comments what each variable looks like. So now we have 3, 2, 1, 5, 4. So nothing's happened to this list, but we've got temp equals 3. Okay? Now, what we do is we go numbers I, so that's this number here, this 3, equals numbers I plus 1, so that's this 2. So what this is doing is this is overwriting this 3 with this 2. So now the list is 2, 2, 1, 5, 4, and 3 is temp. So we've got two 2's in our list, okay? Now what we do is we overwrite this number here with the value that's stored in temp. So we go numbers I plus 1, so that's this value here, equals temp. So we have now we have 2, 3, 1, 5, 4, and temp equals 3. And you see we've swapped this 3 and 2 here. So here we had 3 and 2, and now we've got 2 and 3. Is that clear? Or because I've got a visual demonstration. I've got like a no expense spared visual demonstration if you want to see it. Shall I do it? Yeah, okay. I spent this morning in my office with scissors making this demonstration, so I'm pleased somebody wants to see it. Right, so this is how you swap numbers in an array with a computer. So that's the visualizer. Now here, that seems to be inverted. I'm not sure why it's inverted. Anyway, you can see that. So here we've got the variable temp and the array A. Now in the array A, whoops, we're going to put some numbers. So, whoop, it's a bit like Blue Peter. Okay, so we're going to have 3, what's that, 2, 4, and let's have a 5. Okay, so let me get this right. Okay, so what I want to do is I want to swap the numbers. So here we've got our array, and here we've got temp. Oh, my hand's green. So what I want to do is I want to swap this number 3 and this number 1. Okay, so what I do is I store this number 3 in temp. Okay, so here's another 3. So I store this 3 in temp. So temp is now 3, okay? I then copy this number to here, and we've got 1, 1, and 3. I then copy this number over here, and we've swapped 1 and 3. So if we take these back, you say that was 3 and 1, and now we've got 1 and 3. So the point is that basically we need this temporary storage because we're overwriting the first number with the second number. Does that make sense? Do you want me to do another one? Yeah? I see nodding. All right. So I think I've got enough numbers. So now let's swap 2 and 4. Okay. So what we do is we store the number 2 in temp. Plop. Okay. So now we've got a copy of this. We now overwrite 2 with this 4. So now we've got 4, 4, 2. Okay. Then we copy from temp over there, and we get 4 and 2. And what we've done is basically swapped 4 and 2 via this intermediate variable. Okay? Yeah? Anybody still puzzled? No. Good. So that's how to swap. And basically, the point is, that's how you swap numbers in an array. And that's an incredibly useful thing to do. So, let's move on. So this will swap the ith number and the ith plus 1 number. So, the problem is, at the moment, we're only just swapping 2 numbers. So this piece of code just swaps 2 numbers, boom, like that. But what we need to do is we need to basically swap all the numbers that are out of order. So what we can do is we need to put round this a for loop. And what this for loop will do is it will basically go through each pair, so we can from 1 to 4, so it'll look at those numbers, those numbers, those numbers, those numbers, and this code will swap the ith number and the ith plus 1 number at each point in this array. So it'll swap those, it'll swap those, it'll swap those, it'll swap those. So, what are we missing? Why wouldn't this algorithm work? Yeah? Yeah, so the man's got it there. Basically, this isn't a sorting algorithm, this is a swapping algorithm. It goes through a list and it swaps all the numbers. But if you looked carefully at what the Lego men did, they only swapped numbers that are the wrong way around. Okay? They said, are they the wrong way around? Yes, let's swap them. Here, we're just swapping all numbers. So what do we need to make that decision? If, right? So we need an if statement. So this will only swap numbers that are the wrong way around. So this takes us through the list. So from I equals 1 to 4. So imagine I is 1. So this will say if number at I, so that's 1, is bigger than the number I plus 1, so that's 2, then store the number at I in temp, set the number at I equal the number I plus 1. So this is this swapping thing. We did this paper exercise. Then numbers equals 1, I plus 1 equals temp. So this is just the swapping code. So we're going to go through this whole list of numbers and only swap numbers that are out of order. So, again, there's something missing. So I'm going to pick on somebody. How about you in the black glasses? What's missing? So if you think about the Lego man example, we're going through this list of numbers just once. What does the Lego man do that's different to this? Yeah, they go around multiple times. So Lego men did this swapping exercise again and again and again and again until they're ordered. So what we need is another for loop. So here, we could write some complicated while statement to figure out if the numbers were in order or not, but I couldn't be bothered, that's just too complicated. So I've said, basically repeat from, that should be a 1, sorry, from 1 to 5 times. And so this is basically our algorithm. So let's have a little look at this with an example. Right, so on the right here we've got the code, and rather than initializing just like a set amount of numbers, what I've done is I've used, you'll come on the screen in a minute, I've used the random command here to generate a random list of numbers. So here we've got our loop from 1 to 5, our loop from 1 to 4, our swapping code, and this prints out basically the final result. So let's hit go. Yeah, let's have a look at it. Hit go. So the numbers we had at the beginning were 2, 0, 1, 2, 1, and it's ordered them 0, 1, 1, 2, 2. So that's ordered. So our algorithm has ordered it. Do it again. Yeah. And we've taken the list 0, 4, 2, 4, 1, and we've got 0, 1, 2, 4, 4. So it's ordered it. So I think that is that. Right, so I did this algorithm to start with because it's like the most difficult algorithm I could think of that was a reasonable thing to teach you. And the point about this, the main point I want to take home from this algorithm is when you're writing your own algorithm, because you will write your own algorithms, you just have to make them up at some point, get a clear idea of what it is you want to do. So think of a Lego man example, understand the problem, okay? Then try writing little bits of MATLAB code that work. Then try and extend them and extend them and extend them until your problem's solved. And that's the way to tackle these complex MATLAB problems. So now then, we're going to do integration with a computer. This is a very, very useful technique that all engineers will have to do. So when you're doing things like water flow through strain-shaped pipes and things like that, you'll be able to integrate sort of areas and volumes without any problem at all. So integration with a computer. Now, how would you integrate that? Yeah, exactly. It's a trick question, right? I couldn't do that. I probably could just as I left school, but I can't remember how to integrate that. So what I did is I Googled it, and Google told me that if I wanted to integrate tan to the minus 1x, this is the procedure I'd do. And, you know, this is an okay procedure, and I'd get the answer, and then I could maybe pop that into a computer to do some of this integration. But very often in engineering, you can't actually do the analytical integral. Now, the most simple example of an integral I could find that you can't do is the integral of a normal distribution. So I don't know how many of you have done statistics. How many have done statistics? A few of you? Yeah, so if you look in the back of a statistics book, there's tables of a normal distribution. And it says, if the area under the normal distribution is so much if you have this sort of percentile. And the reason you have these tables is because you can't integrate that analytically. There's no way to do it. So somebody's written a program to integrate this, this integral. And there's all types of things, once you start looking at real-world problems that you can't integrate because there's no nice description of them by hand. So this lecture will basically give you, or this next section will basically give you the power to integrate anything, any function that anybody throws at you in the future. So I'm trying to break this down into really easy sections again. So we're going to integrate the curve y equals x squared. Now, you can all do that in your head, I imagine. And you'd go, oh, y equals x squared. A equals, so integral 0 to 1 x squared dx. You do the integral, and then you come out with a number of a third. Now, the question is, can we find this area in another way? So you've got to remember, integration is basically finding the area under a curve. Well, if you remember back to when you were 16 at school, your teacher probably got you to draw a graph and said, on graph paper, and said, work out the area under the graph by counting all the squares. And you probably sort of counted the squares and got bored and, wrote down something that was a bit close. Well, we can do exactly the same thing to sort of replace integration. So what we could do is to say, imagine we didn't know how to do this integration. We could approximate the area under the curve with these boxes. So this is, I'll give it to you, it's a pretty bad approximation of the area under the curve. But we could draw 3 boxes, and we could go, the area in these boxes is about equal to the integral, like that. But if we wanted to make the approximation more accurate, what we could say is we could say, well, let's use smaller boxes. So there we go, let's use some smaller boxes and use more boxes. Then we just add up the area under all these boxes, and that's the area under the curve, or again, the integral. And if we want to get even more accurate answer, we can just use smaller boxes and smaller boxes until we get a pretty good approximation to the area under the curve. Now, we could do this by hand. If somebody drew a function, you could actually count up the area under the curve by hand. But this is a real pain, and it's slow, and it's no way to do proper engineering. So what we're going to do is I'm going to tell you how to make the computer sum up areas under any curve in the next 10 minutes. So let me just see how we're doing for time. I don't want to rush. That's all right. There we go, 30. So again, we're going to break this algorithm down into really, really small, tiny chunks. So the first thing we want to do is we want to basically figure out the x-coordinate of each one of these boxes to do this integration. Now we can generate an x-coordinate for each one of these boxes using this little while loop here. So I say x equals 0, so that's starting us off at this axis here, so x equals 0. I then say my max, so this is the maximum that we're going to count to, and I've said it's 1 because we're only going up to 1 here. And I've said box width equals 0.01, so this is the width of the box. So that's this width of this box here. I'm then going to say while x is smaller than my max, so whilst x is smaller than this value here, x equals x plus box width, end. So what this will do is this, initially x will be 0, and then we go round here once, and it'll add box width to x, so x will be 0.01. Then we go round again, x will be 0.02, x will be 0.03, 0.04, etc., 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 until we get to 1. So what this has done is generated a list of numbers of x. So it's gone from x from 0 to 1. Okay? So that's the first step. Now, what we're actually interested in is the area under the box. So we need to know the box height, right? So we need to know this height at every location. And the way we calculate the height is quite easy. Well, we know the equation for the line, because I've told you the equation for the line. It's y equals x squared, okay? So to calculate the box height, for every x, we go y equals x times x. So we've calculated the box height, and we've calculated the box position, okay? So the final thing we need to do, or penultimate thing we need to do, is calculate the area of the box. Well, we know the width of the box, so we know this width here, because I've given it to you. Box width equals 0.01. So all we do is we go box area equals y, which is the height, times the box width, And this box area will be equal to the area of this box, then 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 this box, etc., etc., etc. So we managed to calculate the area of each one of these boxes. Now, the final step is to add up the area of all these boxes. So what we do is we define the variable sum. So I say sum, which is just like the summation of everything. Then at each step, we go sum equals sum plus box area. So this will start off here. It'll add this area to this area to the total, this area to total, this area to total, this area to total. And at the end, we just go disp sum. So we've basically written a while loop which does an integration under a curve. Now, the point is that you can replace, so I chose this silly, easy function y equals x squared there, but you could replace that with cos, you could replace that with sine, you could replace it with some crazy, what have we got here? You could replace it with this function that you can't integrate analytically, you could replace it with this function. So now, just using this piece of code here, you can integrate any function that anybody throws at you in the future. So that is something that's seriously helpful for you as engineers. And you'll have a chance to practice in the lab. So the final thing I want to teach you is differentiation. So are there any questions on anything we've done so far? I'm very happy to go over stuff again. We've got a bit of time. Any questions? Okay. Right. So the final algorithm I want to teach you today, so we're 2/3 of the way through it, is on differentiating with a computer. So this will enable you to differentiate any function that anybody throws at you. So, what's next? So if, for example, I threw at you x squared, what's the differential with respect to x of x squared? You'd go, oh, it's 2x. It's very easy, okay? But if I said to you, differentiate sine x times cos x, well, it's a little bit more work, and you do it with chain rule and things like that. And if you were set this in a maths exam, you'd be able to do it. It wouldn't be a problem at all. But very often in engineering, there's functions that you can't differentiate and integrate. And I guess because you're mechanical engineers, you know the relationship between distance, velocity, and acceleration, right? So you differentiate position to get velocity, you differentiate velocity to get acceleration, okay? So you know that relationship. Now, until now, in sort of maths exams, you've been given very easy formulas that said the car's accelerating at this speed with an equation, calculate the velocity by differentiating, or something like that. But when you get to real-world data, so when you actually take data from the car, so imagine we've got this sports car here, and it accelerates, then changes from first to second, second to third, third to fourth, and then it brakes. And this is the velocity, this is the time. If I said calculate the acceleration from that graph, you don't have an analytical function to model that data. So you've somehow got to make a way of basically calculating the acceleration or taking the derivative of this random data set that your maths you can't describe with a mathematical function. So that's why we need to do numerical differentiation. Now, we're going to go back again to what you did at school. So if when you were 16 or 15, your maths teacher said to you, draw a line and then calculate the gradient at x equals 1 or 2. You would do this by putting a ruler on the line, okay? So there's my ruler, this is my ruler. And then what you do, if you're 15 or 16, is you then calculate the difference in y and the difference in x. And then you'd say the slope of the line is equal to dy by dx, so change of y over x. So the slope of the line is the differential. And we're going to use exactly the same technique in computing to calculate the numerical derivative. So this is an algorithm people use all the time. So here's our code to do this. So the first job is to generate this curve of y equals x squared in the computer's memory. So what we do is we define an array of x with 0, 0.2, 0.4, 0.6, 0.8, and 1. So I'm defining this point, this point, this point, this point, this point, and this point. And then I define an array of y. And in this array, I want to populate it with the value that y will be at each one of these x points. So I go, for n equals 1 to 6, so we count from 1 to 6, so 1, 2, 3, 4, 5, 6. Then I go, y of n, so this is the nth position of y, is equal to the nth position of x squared. So what this will do is we'll take this number, square it, put the result here. Take this number, square it, put the result here. Take this number, square it, put the result here, etc., etc., etc. And that will display the result. So now we've got an array of x that is like that, and an array of y is like that. So we've actually just calculated all these points on this graph. So that's the first step to taking a numerical derivative, is to calculate or get some data. Now, we now know the x and y coordinate of every single point on this curve. So all we have to do to find out where this third point is here, I think I'll call that the third point. The third point is there, is we go x brackets 3, so that will give us the x, so this is 0.4. Then we go y brackets 3, and this will give us 1, 2, 3, this 0.16. So this is the x and y coordinate of this point. And if we want to know the x and y coordinate of the fourth point, we go x brackets 4, and then y brackets 4. So this will give us 1, 2, 3, 4, so 0.6, 1, 2, 3, 4, 0.6. So that's the x and y coordinate of that point. Now, we do exactly what we do at school, again. We just calculate the change of y with respect to the change of x. So we go y4 minus y3, which is this distance here. We go yx minus y3, which is this distance here. Or, written out in full, the slope is equal to delta y over delta x equals y4 minus y3, x4 minus x3, or more generally, we can go yn plus 1 minus y of n. So this is y, and this is y of n plus 1. And xn plus 1 minus x of n. So this is the general formula to find out the slope between 2 points in MATLAB. Then we just pop it into our loop. So we go for n equals 1 to 6, so we're looping over this array. Dx equals x brackets n plus 1 minus x brackets n. Dy equals n plus 1 minus y brackets n. So this is working out the change between any 2 points in x, the change between any 2 points in y. Calculate the slope, so just by dividing. And the final step is, so we've done the derivative now of all these points. The final step is just to store this value. So we make a new array called slope, and we just store the result at the nth position of slope, so dy by dx. And that is it. You've calculated now the numerical derivative. So I've taught you how to do numerical derivatives of any function at all. So there's absolutely no need now, realistically, to learn any more differentiation at all in your lives, because this will do it all for you. It might be a bit dry, this differentiation, this integrating, but these are super powerful, and I use these every day. So this is powerful stuff. Are there any questions on anything that's come previously? Please feel free to shout out. I will go through any detail that you don't understand. No? I take that means you're all happy. There is. Okay, right. So the final thing I want to talk to you about is canned algorithms. Now this word canned algorithms is a word I've made up, or it's at least, is that a hand? Is that a hand? No? Oh, sorry, I'm just so keen to hear questions. A bit like an auction. If you move wrong, I'll ask if you've got a question. So canned algorithms. So what do I mean by canned algorithm? It's sort of a slang phrase that's used in computing. And what it means, what the word canned algorithm means, is it means an algorithm effectively in a can. So some engineer before you has done a load of work and made a beautiful algorithm and made it in a really beautiful form that you can use, and either sold it to you or put it on the internet so you can use it, or packaged it in some form that is very useful for you to use. Yeah, so there's our canned algorithm. So you can imagine somebody, instead of you having to write every time the sorting algorithm or the integration algorithm or the differentiating algorithm, you might want to use one that somebody else has written for various reasons. And for example, MATLAB's got this sine function, this sine of x. Somebody wrote an algorithm to calculate the sine of x. Do you know how it works? No. Do you care? No. I just want to use it. So that's an example of a canned algorithm. Somebody has written a really nice piece of code ready for you to use. So in this example, the sine function. So when do you write your own code? So if you want to write your own algorithm, it gives you immense control over what you're doing. So you understand every step of it. And if there's a problem, you can debug it, you can improve it, and you really understand what's going on. And it sort of gives you real power. So that's why I've taught you about algorithms and about sorting and things like that, because it's sort of the first step to writing your own really powerful code. Now, when to use pre-written code? Now, sometimes, for example, this sine function, there's no point in writing your own. Somebody's cracked that problem already. So just use theirs. Just download the code, use it in MATLAB, whatever. Don't write your own new sine function. That's just silly. Now, this is a point I want to get across. So some people spend years of their lives writing these algorithms and improving them and sort of optimize them for you. And you can't write in maybe the hour or 2 hours you've got free. You can't better what they've done in their entire course of their life. So very often, for very hard algorithms and very important algorithms, it's best to buy them or to download them than write your own sometimes. So you've always got to make this judgment call. So, and as Newton said, stand on the shoulders of giants. So stand on the shoulders of people that have done fantastic work before you, and it'll propel your work forward. So here's an example. So this is an example of an algorithm that somebody's written. So this man here, there he is called Tim Davies, and he's from a university in Texas. And he's, guys at the back? And he's spent his entire life, like literally his entire life and all his research career, writing an algorithm to very efficiently solve this equation. So this is like just a normal algebraic equation that's put in matrix form. And he's literally spent his whole life writing a piece of code called sparse-suit that just solves it, inverts this matrix and solves it. And his code is super efficient, it's super fast. Now you might think, well, that's a really small matrix, so I can do that by hand. His code can do matrices like that with millions of elements within seconds. It's super efficient. So that's all he does. And his algorithm is used basically by Google Street View in their calculations of whatever they calculate, in Google Maps, NASA uses it, and also you guys already use it in MATLAB, because whenever you divide one matrix by another in MATLAB, they've actually plonked his code in MATLAB. So the MATLAB people didn't bother writing an algorithm for this. They just borrowed his code, because it's the most efficient way to do it, and he's the expert. And also I use it, and it's a really fantastic algorithm. So my point is, before you start writing an algorithm by hand, look around what other people have done, because sometimes you don't need to write it, you can just like copy it. So there's always this play between the two. Final word on algorithms. If in your third, so this is like just general tip, if in your third and fourth year projects you start to have to write your own algorithms, like do complex mathematics with computers and things like that, get this book. It's called Numerical Recipes, The Art of Scientific Computing. It is the #1 book that all scientists use to solve numerical problems and write algorithms. So this is a fantastic book. It's not for now, but just remember that for later, and you'll think, you go and get it from the library. Brilliant. So that's it. So off to labs, and if you've got any questions, I'm here.